Hi everyone, and welcome to another seminar of Physics Latam. Today we are very happy and honored to have Professor Danfrey with us. He's a total authority on the pure mathematics of theoretical physics, so we are very excited to have him in this seminar series. He is the Chern Professor of Mathematics at Harvard University. He's also the director of the Center of Mathematical Science and Applications, or CMSA. He has a broad mathematical interest in geometry. He has made several contributions to the geometric theory of Dirac operators and related topics in global analysis and topology, as well as to infinite dimensional representation theory. He has also worked with a physicist on geometric and topological problems in quantum field theory, string theory, and most recently theoretical condensed matter physics. He is also a principal investigator of the Simon collaboration on global categorical theories, and he has developed uh, most of the mathematical of Chern-Simons theory. And today he is going to talk about a fully local extension of Chern-Simons theory. Um, Please remember to raise your hand at any point if you have any question, and I will leave you with Professor Dunphy. Please go ahead.
Thank you, Daniel, for that very kind introduction. And thank you, everybody, for coming. Uh, I'm looking at a screen of black squares, except for Daniel. So I encourage any of you who can to turn on your video. It's a lot more human and friendly that way. Thank you. Another Daniel. So people whose name isn't Daniel are also welcome to turn on their screen. So what I'm going to talk about today is joint work with Claudia Scheinbauer and Konstantin Telemann, a long time in coming, but the paper is out. Um, so it's a fully local extension of Chern-Simons theory, and I'm going to explain a lot of background and a little bit of history of what that problem is and how it came about. So so let's start. So the beginning of this story, well, it begins before that, but is Witten's paper in about 1988, I think, on the Jones polynomial and relating it to quantum field theory. And to some extent, in the first part, I'll be telling you a little bit about part of that paper. So the setting is let G be a compact Lie group. And I'll emphasize there are three basic kinds of compact Lie groups. There are finite groups, there are tori, finite dimensional tori, and then the simple, simply connected groups like SUN. And a general compact Lie group is, in some sense, a mix of those three types. And we're going to fix a positive real number. That's a coupling constant. And we're going to pick lambda, which is a cocycle for a class in the fourth cohomology of the classifying space of the group with integer coefficients. So if that's not familiar, we can map that to the fourth cohomology with real coefficients. And this is, in a canonical way, isomorphic to the set of bilinear forms on the Lie algebra of the group, which are symmetric and also G invariant. And if the group G is a simple group, like SUN, then this is canonically isomorphic to the integers. And that integer is what's called the level. But more generally, we'll call lambda the level of this theory. And what one writes down is Yang-Mills. I'll write it out. Plus Chern-Simons. And this is a theory that's given by a Lagrangian density, depending on these parameters, and of course the group. And it has a single fluctuating field. A is a G connection, a gauge field, which is to say it's a connection on a principal G bundle. And this is the Lagrangian density. So as a density, it's 1 over 4 e squared. That's the coupling constant. Fa wedge star Fa. And then we need some sort of inner product in the Lie algebra. Well, let's just say we use the one that we had there. So we can implicitly assume it's positive definite. And plus this other term, which is the Chern-Simons term. So in this talk, I'm not going to emphasize what that really looks like in terms of classical differential geometry. If it's familiar, that would be great. But this is a term which locally looks like a three form, but in fact, it's not quite a three form. It's a three form on the total space of the bundle, and we can make sense of it in the theory of differential cohomology, differential cocycles. But we won't go that route today. But rather, we want to think of the quantum theory after we integrate over the connection. So that's an infinite dimensional space, even an infinite dimensional stack. And there's no rigorous theory for that. But nonetheless, there's a claim. And the first claim, there are several claims. The first claim is that there exists a Wick-rotated three-dimensional field theory. And now I'm going to write it. I'll call it f of e and lambda. And I'll write it and then explain. So it's a map from a Bordism category of 2 and 3 manifolds that are equipped with a Riemannian metric and an orientation. And this maps to the category of topological vector spaces, some particular category of topological vector spaces. So I need to explain a little bit about all of these terms. And I do encourage you to interrupt. You can raise your hand or you can just shout out a question, really. That would be good to give me guidance about where you are. So a little digression. So let's let man 3, but the 3 could be in any dimension, but for today it's 3. This will be a category whose objects are smooth 3 manifolds and whose morphisms are local diffeomorphisms. And so we don't allow all smooth maps, but local diffeomorphisms. If you like, you can just think of embeddings. It would be fine to take embeddings. And then a sheaf on man 3 is a functor, f, that takes to every smooth manifold and it gives us a set, let's say. And if I have a local diffeomorphism, I get a map of those sets, but I get a pullback map in the opposite direction. Plus, it satisfies a sheaf condition, which basically says we can localize and glue along open covers. So it's more or less the usual sheaf condition. So what are examples? Well, one example is that you take a smooth manifold and then you map it to, let's say, the vector space of Q forms, where Q is some integer. So this takes values in vector spaces, and if you have a map of manifolds, differential forms pull back. Another example is to take this to be the set of orientations of M. That's a discrete set. And again, orientations pull back under local diffeomorphism. We could also take it to be the set of Riemannian metrics. We could also take it to be the G bundles, principal G bundles with connection. But now this is no longer a set, but rather a groupoid. And so we have to modify and think of this instead as being some kind of simplicial set or groupoids, or there are lots of choices. But in fact, in this lecture, we're not going to need too much of that. So these are some basic examples. There are also spin structures. That's another example. Again, that's a groupoid, and we'll see other examples. So this I called Riemannian, and this I indicated by the first Stiefel-Whitney class because that's what you trivialize to give an orientation on a smooth manifold. And so here, this Riemannian in W1 refers to these. And so this is the sheaf of those. Now, it's worth saying at this point that there's a notion of F being locally constant. And a sheaf is locally constant here if we have a ball and a smaller ball, and we look at the inclusion of the smaller ball in the big ball, and that means whatever the value of the sheaf, the sections over the big ball, they restrict to the smaller ball, and I want that map to be an isomorphism. That's what it means to say it's locally constant. If I move a little bit, then that doesn't change. Well, so which of these is locally constant? So this is the forms are certainly not locally constant. You can't determine a form on a big ball from the form on the small ball. The same with Riemannian metrics, the same with connections, but the orientations, this is locally constant. And there's a theorem, if we have a locally constant sheaf, this is equivalent to what we call a tangential structure. Which is a space that sits over BO3, really BGL3R, but this is homotopy equivalent to BO3. And that's an idea that was introduced into Bordism theory in the 1960s by Dick Lashoff, and we'll come back and see different tangential structures. So for example, an orientation is a tangential structure, and in that case, this space is BSO3. It's a double cover of this space. Okay, so that explains what this is. Now, the Bordism category, I hope everybody is familiar by now with the point of view really introduced by Graham Siegel and then Michael Atiyah and many others since then of how we think about Wick-rotated field theory, that in this Bordism category, that an object is what? Well, an object is a say Y is a smooth two-manifold. This manifold is embedded in a little thickening, that's big thickening, in a little bit of a thickening, and a thickening to a 3-manifold. And inside that thickening, it's co-oriented. So you can think of that as the y as space in physics, but again, it's Wick rotated, and that arrow as a little bit of an arrow in time into the space-time, which is the thickening. And we have a section of the sheaf. So we have an element of the sheaf on this thickening. So let's call the thickening, I don't know, y hat. So we have a metric and an orientation on this thickening. And those are the objects of our Bordism category. And the morphisms are Bordisms. So let's see, we have 2-manifold like that. And now we have a Bordism like that. And this is X. This is Y1 or Y0, Y1. This X is mapping Y0 to Y1. And we still have these kind of thickenings here around the edges. That helps us to glue Bordisms. And we have a section of the sheaf, which is to say X is oriented and also has a Riemannian metric. Okay, so the idea is that to each of those objects, we attach a topological vector space, typically an infinite dimensional vector space, and we attach to a morphism, we attach a linear map, continuous linear map of those vector spaces. Okay, so let's continue then with the claims. So the first claim is that these theories exist. And that's a big question. That's a big problem. Nobody has really constructed these rigorously as mathematical objects, the way I've said. But let's go on. So the second claim is that the theory Fe lambda is gapped. And I'm not going to try to spell out what gap means, but if you think in terms of a Hamiltonian, then the gap means a spectral gap between the bottom eigenvalue, which we can take to be 0, and the first and the rest of the spectrum. And the gap is somehow approximately 4e squared, some kind of size of lambda. And in fact, if you do this in the case of U1, and you go back to 3-dimensional Minkowski spacetime, which is where the relativistic theory starts, that's a free theory, and you can just write that down. It's a very good exercise, and you can compute what is the representation of the 3-dimensional Poincare group you get. And that shows you the spectrum of the theory. It's a free theory, so that's the spectrum. And you can see the gap. And the gap in that case, lambda is a number, and you can see it's exactly what I said, 4e squared absolute lambda. So that's an excellent exercise. Okay, third claim is that and it's a singular kind of limit, as e goes to infinity of Fe lambda exists and defines a field theory F, let's call it, F lambda, again, on manifolds with a metric and an orientation mapping to topological vector spaces. Okay. So you should think that we have this gap, and that limit is pushing all of the non-zero eigenvalues off to infinity. So this is a kind of low energy limit or a low energy effective theory for this gapped theory. And now comes the crucial claim, again, really in Witten's paper, that the projectivization I'll write it with the bar over it, factors through the Bordism category of 2 and 3 manifolds, but only equipped with an orientation. Okay, so today I'm not going to explain what I mean by the projectivization or projective as opposed to linear field theory. I will say that from the beginning, we're taught that quantum theory is linear. We have superposition of states. But in fact, you then learn that what are the pure states in a quantum mechanical system? Well, they're a projective space. And if you think a little bit more, it's really only that projective space that you need. You don't need the linear space to define the quantum theory. And so, for example, superposition, if I have two points in a projective space, they're distinct, then they determine a projective line. And that projective line are all the superpositions of those two states. There's really not a unique superposition. There's a whole line of superpositions of those two pure states. And, right. So you can go on in field theory and make a notion of projectivization and, or projective theories. And this one comes to us as a linear theory. It's a limit of these linear theories. But that linear theory depends on a Riemannian metric, but only in a very slight way, because its projectivization is independent of the metric. That's the statement. In other words, this is what we call a topological field theory. So a theory is topological if it factors through a sheaf which is locally constant. And these orientations are locally constant, as we said. Okay. So one more thing to say is that there's a measure when you have a projective theory, there's a measure of the obstruction to lifting it to a linear theory. That goes back to Brouwer classes in geometry, to central extensions of groups, all sorts of things like that. It's a cohomology class in that context. And here, it's an invertible field theory. And this is called the framing anomaly. So the word anomaly is used for this obstruction to linearization. And this anomaly is, in this case, well, it's a three-dimensional theory. We're doing three-dimensional physics. The anomaly is a three-dimensional theory, but it extends to an invertible four-dimensional theory of oriented manifolds. And the partition function is the following, that, so call this theory alpha twiddle or something, lambda maybe. And if I evaluate that on a closed oriented four manifold, what I get is a number. It's a root of unity. And the number is 2 pi I c. This c depends on the group and the level, divided by 24 times the first Pontryagin number of W. So that's the formula, where C is a certain number. It's a certain rational number that we can compute from the level. Okay. So that's the statement. Maybe I won't give the formula for C. There is a general formula for C, but that's the statement. Okay, any questions before I go on? Okay, so we started with, I'll draw a diagram. We started with this sheaf of Riemannian metrics and orientations. And there we have this theory, which is F E lambda. And this, of course, maps to the sheaf of just orientations, just forget the metric. And here, when we take the limit, e goes to infinity, we get the theory F lambda, which doesn't drop there, but its projectivization drops there. Okay. And so we can think that this is a projective theory, which is topological, and it has a linear lift, but the linear lift is not topological. It depends on the Riemannian metric. And so we can ask a question to use topological methods to construct this projective theory and a linear but topological lift, which I'll call Z lambda. So again, we have a linear lift of this topological theory, but that linear lift is not topological. And what we'd like to do is have a topological linear lift. Okay. And so how are we going to do it? Let's go to a new page. So the way Witten does it in this language is to pass to another sheaf that sits over here of manifolds that include a Riemannian metric, an orientation, and something called a P1 structure. So I want to emphasize that the first Pontryagin class is entering the story here through this framing anomaly, the obstruction to lifting this projective theory to a linear theory of oriented manifolds. And we can kill this obstruction if we kill P1, and that's what this P1 structure does. I will explain what a P1 structure is in a minute. But here there's a particular invertible field theory, gamma C. This is invertible. And again, I'm not going to say too much about it in this talk, but it's essentially a classical Chern-Simons theory, and it's really the one in the 1973 paper of Chern and Simons. It's one that they discuss in some detail. But there's a little bit of a extra thing going on because of this P1 structure. And this is designed, this particular theory is designed so that sitting in here, we have the sheaf of oriented manifolds with a P1 structure. And this is, again, a locally constant sheaf or a tangential structure. And the idea is that if we tensor now this F lambda which was our linear limit. So F lambda, I've been pointing at Fe lambda, but I meant the limit as e goes to infinity is a linear theory here. If we tensor that theory, maybe I should have erased that. If we tensor that theory with gamma c, then the metric dependence drops out. But in exchange, we have this P1 dependence. So that's the trade-off. And this now is Z lambda. And this is what topologists usually call Chern-Simons theory. Okay. All right. Any questions about that? So these two theories are topological. The other two theories are not topological, but they're not that far off from being topological. They're just off by something invertible, essentially. Okay. So I'll remark now that this is not the only linear lift of this projective theory to W1 P1 manifolds or oriented P1 manifolds. There are, in fact, some invertible theories here. There's, in fact, a cyclic group of order 6 of invertible theories here that we could tensor Z lambda by and not change the underlying projective theory. So that's something we'll see a little bit later. And let me just remark, but in the interest of time, not say anything more. There is a variation with spin structures. And in this language, a spin structure is a W1, W2 structure, and we just have to join the second Stiefel-Whitney class everywhere into the story. But we have to say what Chern-Simons means in the spin case, what kind of levels there are, and so on. But there is a spin analog of this. Okay. So again, the main problem that's been there since the late 80s is to construct, using topological methods, to construct this theory. Now, so far, we've seen this theory as what I would call a 2-3 theory, meaning it's a theory of 2 and 3 manifolds. And that's not completely local. We would like something to be fully local, meaning that we can not only cut 3 manifolds in codimension 1, but we can cut in, so to speak, 3 directions to cut it in terms of balls. And that's the idea of an extended field theory, or eventually a fully local field theory. So again, I'm not going to, in this lecture, spell that out. There are plenty of texts in which you can do it. But right around the same time as Witten's story is Reshetikin and Turayev, really about the same time. And they construct a, well, let's say unitary, I would call 1, 2, 3 theory of oriented manifolds. And then instead of P1, it's in a sense a kind of signature structure. But again, in this lecture, although if you look in our paper, then we do explain this, but I'm not going to say what a signature structure is in this paper. But what they construct is Z lambda, I guess, from now an extended Bordism 2 category of manifolds with orientation and signature structure. And now we need a 2 category over here, which is a 2 category of linear categories. And again, there's a lot of technical details that are very important that go into saying exactly what category you have here. There are many different choices, and they matter. But again, I'm not going to tell that. So in particular, we can evaluate this on the circle. So now we have a linear category, which is the value of this theory on the circle. So this is a key object in the theory, and T inherits from the Bordism category. So from the geometry and algebra of this category, whatever structures we have here are passed to the values of this theory. This map is a homomorphism. It's a functor in the sense of categories, but these are also symmetric monoidal categories, importantly. Here we have disjoint union is the monoidal structure. Here we have tensor product of vector spaces, and disjoint unions go to tensor products. So, for example, if I write down this Bordism here, so I'll draw a careful picture once. So this is a disk which has two smaller disks removed. And I'm not going to draw the little germs of the higher dimension of the around those boundaries, but I will draw the co-orientations, which is to say that these two inner ones are incoming and the outer one is outgoing. And this behaves in the Bordism category like a product. We would say that the circle is an E2 object in the Bordism category. And so what this gives is, in fact, a braided monoidal or tensor structure on this category T. So there's a commutativity by braiding the two inner circles, one around the other. And there's another structure, which is a ribbon. It's again a structure. And it comes from looking at the diffeomorphism group of the circle. But again, it's a circle now with an orientation and a signature structure. Okay. And these structures together obey some constraints that imply that T is a modular tensor category called an MTC. And in fact, what Reshtikin and Turayev do is to construct the theory starting from this modular tensor category. So given a compact Lie group and a level, we could ask to construct a modular tensor category. In fact, that's an open problem. So maybe it's worth writing down question. Given compact Lie group and a level, we want to construct a modular tensor category T depending on G and lambda. And there is no such construction that I know. In the three different cases I said, the three special cases of a finite group, of a torus, or of a simple group, then there are constructions. There are constructions, uniform constructions of pieces of this. For example, there's something called the Verlinde ring that one deduces from that. And that does have a uniform description in terms of the Lie group and the level. But to construct the full MTC, that's still an open problem. So let's say one. And the other thing we might like is a fully local version of Z lambda that goes from Bordisms 0, 1, 2, 3 with some structure into some 3 category. And I'll just write this as board 3. Okay. And this is the problem that we solve in this paper. So we do construct this locally, this fully local extension. Any questions about that?
This construction is for closed manifold?
Which one? The one that we do?
Yes.
Well, yeah, it's this Bordism category. Remember, when we were just at level two, so to speak, two and three manifolds, then the objects are closed two manifolds, and the Bordisms are already not closed. Closed means compact without boundary. So this Bordism is compact, but it's not closed. It has boundary. And when we go to higher codimension, then we're going to allow ourselves pictures. Like, for example, we might have some points, and these points might evolve. Okay, maybe I should draw a real picture. So we might have points. These points might evolve to points like this, but we might have another point here, and then we could have something like this. So this, in the Bordism category where we have 0, 1, and 2 manifolds, then we could already have, this is all, a two-dimensional surface. But this two-dimensional surface is certainly not closed. It's compact. But it not only has boundary, it has corners. So these points are corners of codimension 2. And when we go to the 0, 1, 3 Bordism category, then we can have corners of codimension 3. So everything in here, all the objects and morphisms are compact manifolds, but they're allowed to have boundaries and corners. Okay. And so that's important to get the full power of the locality of the field theory where we can cut and paste. So we want to be able to cut and paste not just along boundaries, but also along corners. All right, good. Other questions? Okay. So, so as I said, this key object in the theory, this T, it comes to us as a category. It's the value of this three-dimensional field theory in codimension 2, that is to say on a closed one manifold, 1 being 3 minus 2. That's why I call it codimension 2. And so that is a linear category, but it gets this extra structure. And I want to not think about the ribbon structure for a second and focus on the braided tensor category. And this braided tensor structure satisfies a non-degeneracy. So T has a braided tensor category, and we'll call it braided tensor category, satisfies a non-degeneracy condition. And what is it? It's that the set of all objects in T such that if I braid this X with another object Y, and I compose with the braiding of Y with X, and I ask that this be the identity on X tensor Y in the category for all objects Y, that this is equivalent to just multiples of the tensor unit. You should really think of this as multiples of the tensor unit in the category T. Vector spaces times the tensor unit. So X are the objects that braid trivially with every other object, and certainly the transparent X, the identity, braids trivially. That's part of the definition of a braiding. But in general, we can look at all the objects that do. And in general, this subcategory of X's forms actually a symmetric monoidal category. And this is called the second or Muger center of T. And that center is trivial in this sense. So that's a non-degeneracy condition. And in fact, there's a theorem, which I believe is, again, due to Muger, that says that T is non-degenerate as a braided tensor category if and only if T is invertible in some category of braided tensor categories. So this is now a 4 category, and this is symmetric monoidal. And saying that T is invertible is saying it's in GL1. Those are the invertibles, the maximal groupoid, the invertibles, Picard groupoid, of invertibles inside there. Okay. So again, you'll have to look in the references to see how you define this 4 category. The objects are braided tensor categories. The morphisms between 2 of them are themselves tensor categories, but they have an action of the braided tensor categories. They're bimodules for the braided tensor categories, but they are themselves tensor categories. And then we keep going. We get bimodules for those tensor categories compatible with the braided tensor categories. Finally, we get maps of those bimodules and then natural transformations of those maps. And so you can see that you get 4 layers of structure here. And that's why we get a 4 category. So the algebra, if you haven't seen it, this higher algebra gets a little bit complicated, but that's what reflects in the algebra on the Bordism side that we're cutting. We have 4 layers of structure, 4 composition laws from this kind of cutting. Okay. Again, any questions? Okay. So we're going to need to know a little bit about these invertibles. And so here we have this 4 category, these braided tensor categories. Certainly not every braided tensor category is invertible. And what we've done is restricted to the objects that are invertible, meaning invertible under tensor product. This is a symmetric monoidal category. We have a tensor product, so we have a notion of what it means for an object to be invertible. But also all the 1 morphisms, 2 morphisms, 3 morphisms, 4 morphisms are also invertible. So having all the morphisms invertible says we have a groupoid. It's a higher groupoid, a 4 groupoid. And then, in addition, we have this symmetric monoidal structure, and the objects are invertible. So if we have a groupoid, then that's equivalent to a topological space. That's the first construction we learn in algebraic topology, taking the fundamental group, but really fundamental groupoid, and then taking higher versions. And this, we can go backwards and go from here to a space. And then this additional symmetric monoidal structure and the fact that the objects are invertible, that's called a Picard groupoid, brings us to an infinite loop space, or equivalently a spectrum, a connective spectrum. So this is a connective spectrum. And in fact, because we only have 4 layers of structure, it actually only has 4, well, plus the bottom, possible homotopy groups. So there's pi naught, pi 1, pi 2, pi 3, pi 4, which are the only possible non-zero homotopy groups. And it works out that the middle ones are all 0. The top one is the scalars, but the invertible scalars. That's easy to see. And the bottom one, well, these are some sort of equivalence classes of braided tensor categories. And this W is what that group is. So that's some abelian group, discrete abelian group. And that's called the Witt group of braided monoidal categories, invertible. It was introduced by Davidov, Muger, same Muger as before, Nixtrick, and Oster. And a non-degenerate or invertible braided tensor category is 0 in this Witt group if and only if T is the Drinfeld center of F for some fusion category, F. And the 3 category of fusion categories we denote this way. So this is called the Drinfeld center. Okay. So remember, our goal is to construct a fully local theory that extends this 1, 2, 3 theory of Reshtikin Torayev. We want to extend to a fully local theory here. And the key object, we said, is this non-degenerate braided tensor category. That's what's attached to a circle. So we need something one more level to attach to a point. And we might think what we could attach to a point, instead of being an ordinary category, is a fusion category, because fusion categories make a 3 category that's precisely the right level of structure, amount of structure, to be attaching to a point in a 3-dimensional theory. And what this suggests is that we can do that in the case when T is 0 in the Witt group. And in fact, that is true. And so, right. So in that case, the case that our braided tensor category, our non-degenerate braided tensor category, is the Drinfeld center of a fusion category, then there is a fully local topological field theory from board, maybe we should call it Z sub F, from board 3 of F, well, something, to the target, which is fusion categories. So this is, again, the 3 category of fusion categories. And there's a very important paper of Chris Douglas, Chris Schomer-Priest, and who's the third author? Noah Snyder, which talks about this fusion category in detail and constructs then this theory, which sends a point now to this fusion category F. And these theories are called, well, so I should write Douglas, Schomer-Priest, and Snyder. And these theories are called Torayev-Virov theories. So, yeah. So these theories are fully local. It's a kind of question about what tangential structure. Do we need an orientation? Do we need something else? And our paper addresses that to some extent. So, for example, we prove that if this has a spherical structure, that then we can make this theory on oriented manifolds. But I'll explain, I'll about the cobordism hypothesis, which tells us, at least at first, that this is a theory of framed manifolds. But we can do better than that. Okay, but that's only the case when we have t equals 0 in the Wick group. And we want to do this fully local extension of all of these Resh-Tikin and Turayev theories, which again are defined somewhere as 1, 2, 3 theories, starting with this modular tensor category or dropping the ribbon with a braided tensor category, but one that is non-degenerate. Okay. And so let me, before the break, end with one more observation, which is supposing Z is a theory, of the type we've been discussing, and at least a 1, 2, 3 theory. And let's suppose that beta is an invertible theory of the same type. Then we can consider the theory Z tensor beta. It's the same underlying projective theory. We're tensoring by something invertible. That doesn't change the projectivization. But we can evaluate on a circle. That's where we get this non-degenerate braided tensor category. Well, the tensor product means that we've taken Z of S1 tensor beta of S1. And what is this? Well, this is T, whatever our braided tensor category is, tensor beta of S1. But this beta of S1 is some linear category. It's an invertible element of linear categories. And there are no non-trivial ones. There are no invertible, interesting linear categories. They're all isomorphic to vect. And so that means that this is isomorphic to T. And what it means is that given T, given this non-degenerate braided tensor category, we can't hope to construct this theory, this linear theory uniquely. We can only hope to construct it up to tensoring with invertibles. And so we're going to see that this indeterminacy up to tensoring by some finite cyclic group, it'll be of order 6 of invertibles. That we're going to see in the construction. So the idea is that we can't carry this out inside fusion categories, this 3 category, because not every non-degenerate braided tensor category is a Drinfeld center. So we're going to enlarge this. We're going to embed this in a much bigger category. Essentially, we want, for each element of this Wick group, we want to introduce a phantom category, like a fusion category, whose Drinfeld center is going to be the given T, where T is in this particular Witt class of these. That's the idea. So we have to see how to construct that 3 category, and then we will necessarily encounter some extension of the Wick group because of this indeterminacy by invertibles. All right, so in the next part, I'll say a little bit about that construction and state at least a few other things we do in the paper. But why don't we have a little break now? Okay, well, thank you all for returning. Before I start, are there any questions? It's hard to know anyone's behind all those black boxes I'm looking at. But I'll trust you're all there, understanding every word I've said, since you're not asking questions. And so let's move on. I don't know how I'll act on that assumption, but I'll think about that in the next 45 minutes too. Okay, so perhaps it's a good idea at this point to remind you of the cobordism hypothesis. And the cobordism hypothesis applies to fully local topological field theories. Okay. And so if we have a fully local theory, in this case, I guess I'm calling it Z, from board 3, with some locally constant sheaf, into some 3 category. So this is some locally constant sheaf or equivalently tangential structure, and this is some symmetric monoidal 3 category. Then we can map these theories. So these theories are sort of Hom tensor, meaning they're symmetric monoidal functors from board 3F into C. We can map it into C by taking such a theory and just evaluating on a point. Again, the point is embedded in a 1 manifold, embedded in a 2 manifold, embedded in a 3 manifold, just little germs. And on that 3 manifold, we have a section of whatever sheaf this is. So we pick some standard point. We really have the whole family of points. And really, the theorem says that it's determined by what happens on that family of points, all those points. And so the theorem says that this is an equivalence of some sort. Okay. So the theory is determined by its value on a point, but what's more, that we can construct the theory from its value on a point. And if our tangential structure are what are called 3 framings, then it's very clean. There's only 1 point to look at, and the theorem says that it's determined by the value on that point. But if we want other tangential structures, like orientations or orientations together with P1 structures, then we need to do a little bit more than specify this. So this is how we want to construct the theories. We want to apply this powerful tool, powerful theorem called the cobordism hypothesis. And to do that, well, we have to construct this category C, which is an extended version of fusion categories. So extended fusion categories. That's what we're going to construct. And we need to be sure that the objects in this category are finite enough. So that's internal to the theory of symmetric monoidal categories, or the theory of duals and adjoints. And that's, of course, an important part of this cobordism hypothesis. That's the key concept that Baez and Dolan in 1995 put their finger on. And later this was proved then by Hopkins and Lurie in the 2-dimensional case and Lurie in general. And it's something that people are still working on to really get a complete proof. Okay. So what's the kind of idea of the construction of these extended fusion categories? Well, we're going to take our non-degenerate or invertible braided tensor category, and we're going to embed it inside what we'll call pick of fusion categories, which are invertible modules over fusion categories. So fusion categories form a 3 category, but it has a tensor structure, and we can look at modules over fusion categories, module category. So to such a category, we'll have FT, which is going to be the 3 category of fusion categories equipped with an invertible T module. structure. So I said in words that it makes sense for a fusion category to be a module over a braided tensor category, and that's the notion that we're using here. So T itself is an example, which is the regular module. So anytime you have an algebra of any sort, ordinary algebra, vector spaces, or higher algebras, it always acts on itself on both the left and the right by multiplication. And so we get a canonical left module and a canonical right module. They're invertible. And that's, in a sense, the trivial invertible algebra. It's just the regular module. It's the regular module. So that's one thing to say. And if we take modules over the tensor product of two braided tensor categories, this is isomorphic to modules over T1 tensor modules over T2, where T1 and T2 are these non-degenerate braided tensor categories. So we'd like to form the sum over equivalence classes of T's in this wit group, the different wit classes of these invertible braided tensor categories. We'd like to form the sum of these FTs. And we'd like this to be our target 3 category. We'd like this to be the C that we use as the target for these extended Reshtikin-Turayev theories. But we need to make this into a symmetric monoidal category. And to do that, we have to, we need to do something to do that. Okay. So maybe this is a good time to at least state our main theorem. Again, I'll have to defer to the paper for all details, but let me state the main theorem, which is that there exists a symmetric monoidal 3 category, which we call extended fusion category, such that several things hold. So first of all, this category has all duals and adjoints. So it's finite enough that its objects define topological field theories, at least framed theories. Furthermore, it has a direct sum decomposition into these pieces where W ranges not over the Wick group, but over some central extension, or a central extension of the Wick group by the cyclic group of order 6. And you can think of that cyclic group of order 6 as being the cyclic group of order 6 of invertible field theories in this dimension of a certain type. Okay. So if we have objects in some of these components, and these are in distinct components, then Hom in this category between these objects only consists of the zeros, zero homomorphism. So it's not empty. This is a linear situation. Like you don't have an empty vector space. You always have a zero vector. And so here we have 0. So I'll come back and comment on this. One comment is that it follows from 2. Saying you have a direct sum is really saying that. But I want to emphasize this particular point. that the different components don't communicate with each other in a non-zero way. Okay. Furthermore, this W tilde is an abelian group, and the zero component is the three category of fusion categories. So this is really extending fusion categories. Each of these FWs is an invertible F module. And if T is a non-degenerate braided fusion category whose class is W, then this FW is equivalent to modules over T, the invertible T modules. So again, these labels are really in this central extension, but they map to an element of the WIP group, and it's that we're talking about. So there are 6 components here that map to each WIT group element. And what are those 6 components that map to the trivial component, which is to say the ones that are Drinfeld centers? So that's this kernel mu6. So let's call that zeta. If zeta is a 6th root of unity, then we can identify that component with just the category of fusion categories is generated by an invertible object called U zeta. Okay, so there's some invertible. And this invertible generates an invertible 3D topological field theory that factors uniquely to a theory of W1, P1 manifolds. Okay. So that identifies them with this group I alluded to of invertible theories like that. Okay. There's some universal property as well. So that's the theorem that characterizes, these properties characterize this 3 category. And the statement is that once we have that, we can use it to construct these topological field theories, essentially from the T, what in the original construction is a modular tensor category, but more generally a non-degenerate braided fusion category. And but there are 6 of them for each, and we have to specify really a point in this central extension to get that. Okay, so there's more about descending those with different tangential structures. I'll mention that at the end. But let me make a point now about this non-communication of these different theories. So, right, so this is property 3. So 3 implies that if the Witt class of T is not 0, then Hom in this extended fusion category from, well, the trivial, the tensor unit, say, into, well, some object X is 0. If, okay, so let's say W is this and X is in this component W. So if we're in a non-zero component, then there's no communication Now, what in field theory terms does something here mean? Well, you can think of those HOMs as being like domain walls. So, right. So here we have, let's say, a domain wall. Here we have the theory given by X, which has this Drinfeld center T. And here we're going to have the trivial theory. Well, the trivial theory may as well not be there. And then you can think of this boundary here as being not a domain wall to the trivial theory, but you can think of it as being actually a boundary theory. And what this says is that unless we're in this trivial component, then there are no non-zero boundary theories for this three-dimensional theory. So that's something actually Constantine and I proved in a different paper a while ago. And so the import of that is that often people think that what you should attach to a point in a topological field theory are some kind of higher category of boundary theories. That's a statement that people make. And that's not correct. One has to distinguish between this idea of being fully local, attaching something to a point, and boundary theories, or more generally domain walls, or more generally defects. So whatever category is attached to a point, that point you can think of as the link of the boundary. The link of the boundary in the sense of manifolds, the link of a submanifold is the sphere in the normal bundle at any point. The sphere in the normal bundle in codimension 1 is a zero sphere. But we should, since on the left, this point is sitting in the trivial theory, it's not really there. We just have one point. And we can evaluate our theory on that link, that point, and we'll get something. But we don't know what the objects in a given category are. They're just abstract algebraic things. But what a boundary theory attaches to a point, so to speak, is not an object in the category, but rather it's an object in HOM from 1 to whatever is attached to a point. And in a 3 category, HOM from between two objects, that's a 2 category. That's always a 2 category. So we don't know what the objects are. They don't form 2 categories. We don't have any map from our category to some 3 category of 2 categories, but we have this HOM space. So while we can have this 3 category, we can have the 3 category and still have that there are no non-zero boundary theories. And that's exactly what this is saying. Okay. So I think that conceptual point, which I think in the past I've also conflated, I think that might have held up a little bit, this understanding of how to make theories fully local and separate that from the idea of the boundary theories, or more generally, defects. Okay. So, yeah, so maybe to give you an idea of the flavor of this construction, let's do a toy construction. So the construction we make is a construction in, so to speak, higher algebra. And here we have a toy construction in ordinary algebra. So let's suppose that A is a discrete no topology algebra, meaning an algebra in vector spaces, and G is some discrete group. And let's suppose that for every group element, we have attached a G, which is an invertible, say, AA bimodule. And we'll define a kind of cross product of, in this case, to be the direct sum over the elements of the group of these invertible bimodules. And now we want to put an algebra structure. So we want an algebra structure, I don't know, call it B, want an algebra structure on B. So that's similar to what we said over here, where we want to form this, we have this group, the Wick group. We have these invertible modules. We can turn them into invertible bimodules because this is braided, which is a kind of commutativity. And we'd like to form this. So that's exactly the analog of this here. But this is in a much more familiar setting. And so we need, of course, multiplication maps from AG1 tensor AG2 to AG1, G2. And in fact, in this case, we have such multiplication maps because we have this kind of thing for these modules. We know what AG is. But they need, importantly, they must satisfy associativity. So you can think of that as some sort of coherence of these various maps, among these various maps. Okay. So that's the thing that in our case, in this higher case, we don't know. We don't know how to make these coherent. That's what we'd like to do. So how do you actually, more professionally make this construction? You don't just say that these invertible bimodules come from nothing. So the usual construction is that you're given a homomorphism from G into automorphisms of the algebra automorphisms of this algebra A. So this is some homomorphism. And now we can build this AG. If I call this, I don't know, alpha, then we build AG. We're going to have A operating on both sides. And so just as a vector space, we take this AG to be equal to A. And on one side, I don't know which, say the left, we can take ordinary multiplication. But on the right side, we want to take the multiplication and twist it by the automorphism. So in other words, if we have an element B in this bimodule and we have A left and A right here, then I guess the equation we want is that A left multiplying B multiplying A right is equal to A left times B times this automorphism applied to, the automorphism we get from G applied to A right. That's the kind of formula. And when you do that, then you can see that you can introduce a multiplication on this B that makes it into an associative algebra. Now, in our case, we want not just the analog of algebras, but you see, we want this 3 category here that we construct, therefore this extended fusion category, to be a symmetric monoidal category. And that's the analog of having a commutative algebra. So we want not only an algebra, but commutative algebra. So we want this B to be commutative. Well, how does that occur? Well, first of all, we need that A is commutative. A is a subalgebra of B, so certainly if B is commutative, A is commutative. Then it's not hard to see that we need the group G to be abelian. And we need that each of these bimodules is central, meaning that if we operate on the left, it's the same as operating on the right. And that means it's equivalent to an A module, a one-sided A module. So when we have a commutative ring, we have one-sided A modules. And the A modules, the set collection of A modules is a symmetric monoidal category. Right. So if we want to be in the commutative world, and that's where we want to be in this higher situation, then we want an abelian group. We want to start with something commutative and construct something commutative. And so we're going to do it from A modules and then make the corresponding central bimodules. But again, we need this map like this. Okay. So, right. So we can generalize and we get A is a symmetric monoidal or commutative category of algebras in a higher category. G, instead of being a commutative group, is going to be a connective spectrum. That's the kind of higher analog. And this alpha is going to be a homomorphism from G into pic A, which is to say a spectrum map, where pic A is the spectrum of these invertible modules. And then we can make a construction. We want to get G. We want to get this to be symmetric monoidal. Okay, so that's the kind of idea of how we construct it. And at this point, I've given you maybe enough of a kind of background and introduction to really try to tackle the paper, which just gives the constructions and the proofs. Okay, so well, okay, so I'll just give a basic idea of the proof, then, is to take the algebra A to be this category of fusion categories. So these are algebras in categories. So now we need some facility with this higher algebraic story. But A plays the role of the algebra we had before, the fusion categories. And G, well, the group we want is this Wick group, but we want it as a spectrum. So this is the Eilenberg-MacLane spectrum built from this group. And now what we want is we want a spectrum map from here into, well, we want pic F, we want invertible F modules. And remember that the way we got invertible F modules, it's here somewhere. Thought I wrote it somewhere. Maybe I didn't write it. Here it is. That we get invertible F modules from these non-degenerate braided fusion categories. Because if we have a non-degenerate braided fusion category, then we can look at the invertible F modules of modules over that braided fusion category. And so, in fact, we're going to construct a map to GL1B and then use this kind of inclusion into that. Okay. So that's the map we want to construct. And we don't have that map. But what we do have is that right, that for any x, which is, say, a connective spectrum, we have a map from the sphere spectrum, tensor pi naught of x into x. So we have to say kind of what that gadget is, but you can build that gadget by making a free resolution of this group. So what we have then is the sphere tensor, well, pi naught of our spectrum that only has pi naught of that spectrum is the Witt group. And so what we're going to have, this is a kind of Hurewicz map into this Eilenberg-MacLane spectrum. And right, we get a map phi into GL1b. How do we get that map? I think that's the map. Sorry. We apply this idea to the spectrum GL1b, and that gives this map phi. This is a Hurewicz map, which we always have. And the idea is that we want to factor this. That's the map we want. And so now we have a standard problem in algebraic topology of factoring a map, an obstruction problem. And so we have to evaluate what the obstructions are. And we're not going to find that they vanish. But what we'll find is that if we lift to a central extension of W, that obstruction problem will tell us what extension to take. And then we get such a map. So that's exactly how the proof goes. And that's exactly how you construct this crucial central extension that allows you to make the theory. Okay, so that's just an idea of the proof. Again, I defer to the paper for all the details. And really, that's only the first few pages of the paper. The paper has a lot more in it. And so let me just say a little bit in the last 10 minutes or so. Let me say a little bit about what else is in the paper. So first of all, we do a super extension, which is a sort of extended superfusion categories. So there's a notion of superfusion categories and corresponding topological field theories. And again, we want these Chern-Simons that are called spin Chern-Simons, and more generally for superfusion categories, for super braided fusion categories, we want analogs of those theories. So there is a super version of this, of everything I've said. So for example, there's a super Witt group, and in this case, we get an extension of the super Witt group by, instead of 6th roots of unity, by 24th roots of unity. And so again, we get this ESF is a direct sum over W's now in the super version of this of some component there. So we get a similar story. But there are more homotopy groups to deal with in the obstruction problem. I think Daniel asked about me about in the break. Okay. Then the idea is that given X, which we could take in the super case, that includes the non-super case, of course, then we construct a topological field theory we called Z hat, I think, from board 3. So again, fully extended, but now 3-framed theories. So remember, the Bordism category consists of 3 manifolds. Those are the top-level Bordisms. But in dimensions below, we always have these thickenings to 3 manifolds, these little thickenings, or even germs of thickenings. And this tangential structure says we have an ordinary parallelism on all those 3 manifolds. That's what it means to have that. So for example, a closed-oriented surface typically does not have a 2-framing. A torus has a 2-framing, but a sphere does not, famously, 2-sphere. But they all have 3 framings because you can embed an oriented surface in 3 space and just restrict the standard three framing of three space. And now a change of framing that preserves the underlying spin structure is local, meaning that we're on a three manifold, and now we have a framing, just a basis at each point, and I can in a ball, so in a disk, mod its boundary two sphere, we can change a framing by just changing in that little thing. And so that maps really to the spin group, spin 3, which is topologically a three sphere, if we preserve the underlying spin structure. And so these are given by integers. So we could ask, if we're on a closed manifold or even other invariants, it's a local thing, that how does this integer change, one unit of this integer change the invariant? Changes the invariant by a number mu, which is written as the exponential of 2 pi I over 6 times some c. This is a priori a number in C star. And so a priori the C lives in the complex numbers mod 6z. And this C is related to the central charge that I talked about in the context of these Chern-Simons theories when I began. So when we have Yang-Mills plus Chern-Simons, we have a rational number whose formula I didn't give you, which is the central charge of that theory. And ultimately, central charge comes from two-dimensional conformal field theory. Two-dimensional conformal field theories can live on the boundaries of these three-dimensional theories. And we do prove a theorem that relates this kind of central charge with the central charge coming from those boundary conformal field theories. Okay. So that's what the cobordism hypothesis gives you in the first instance, is this theory of three-framed manifolds. Oh, I didn't even write it. Sorry. This goes to these extended superfusion categories. That was the whole point, was to construct the codomain for our fully local theories. Okay. But three framing is not really the best tangential structure. And in fact, if we go back to towards the beginning of the lecture, remember that we saw these P1 structures appear. And really, these W1, P1 structures are the most natural, at least starting from Chern-Simons or Yang-Mills plus Chern-Simons. So, so we now want to consider descent to W1, P1 structures. And so we proved the following theorem in the paper. And again, it's a kind of homotopy theory question in the context of the cobordism hypothesis, to find some invariance on the object you're attaching to a point. So in this case, invariance about these objects. So it's a mix of homotopy theory and the higher algebra of these non-degenerate braided fusion categories. So let's suppose that we have an object that we're attaching to a point. And now let's choose a fourth root of this number. So remember, our C was defined mod 6. This lifts it to mod 24. Then this theory descends in two distinct ways. to a theory of W1, W2, P1, spin P1 manifolds with, of course, the same 3 category as target. So again, here I'm doing the bosonic case, and we have W1, P1. But if we had put in the spin structure, which we're doing now, then we would have as well W2, and that's what we see here. Okay. So there's a certain invertible theory that these differ by. And one comment that, again, I was asked about by Daniel in the break is that our story has no unitarity. We haven't incorporated unitarity. We worked out the theory without unitarity. And maybe a remark is that if you think of a topological field theory as a representation of a topological Bordism category, a linear or projective representation, in representation theory of groups, one studies representations separate from unitarizability. For compact Lie groups, there's a theorem that every representation is unitarizable. In fact, uniquely in a sense. So you may as well study unitary representations. But if you start studying representation theory of groups like SL2R, then it's not true that every representation is unitarizable, and unitarizability is something you study separately. So the same with topological field theory, the representations here. And if you put in unitarity, then we can imagine that, in fact, you wouldn't encounter these 2 different ways. The field theory that you have to tensor by, the invertible field theory that passes between these 2 different lifts, is not unitary in the appropriate sense. Okay, so we get theories of, this is not the same as 3 framings. It's not far off. In fact, if you have spin manifolds, then you have kind of, in this dimension 3, you have a P1 over 4 defined. And if we instead did P1 over 4, then this would be the same as 3-framed. So it's very close to 3-framed, but there's some work to do to descend, and there's data to supply, which is this 4th root. Now, you remember also that way back, maybe here, no, here, I said that when we have this Reshtick-and-Turayev theory, what's attached to the circle gets a braided tensor structure, and in fact non-degenerate, that's what we've been using, but also this ribbon structure. And our story so far has not brought back the ribbon structure, and this theorem then brings back the ribbon structure. And it says that supposing we have this object, which again, now it's going to be not super, notice. So just a fusion category, extended fusion category. Then a modular, but think of that as ribbon, structure on T, which is the value of this theory on the circle. But these are the 3-framed circles, and so there's a bounding and a not bounding. And here we want the bounding one. That's the one that has the braided structure. Descends this framed theory, Zx hat, to Zx, which is now on board 3. We don't have spin structures. We took ourselves out of that situation by taking ourselves out of super into extended fusion categories, which in particular determines a distinguished 4th root of this number, or if you like, lift of the central charge, originally defined mod 6 to mod 24. Okay. So this is the story that's really the closest to the Reshtick and Turayev, because in Reshtick and Turayev, you start not just with the non-degenerate braided fusion category, but with a modular tensor category. So it has this ribbon structure. And this says we get exactly what we saw from Chern-Simons, from the physics motivation. We get a theory of W1, P1 manifolds. And it has a central charge, which is defined mod 24. But here we get it as a fully local theory. Okay, and let me mention one last theorem. And in fact, it echoes a theorem in that paper I mentioned with Constantine, where we talk about the non-zero boundary theories. There we characterized the condition of being a fusion category in kind of higher categorical terms. Namely, a fusion category is three-dualizable, so it's finite in some category of tensor categories, but it's equivalent to saying that it's finite in that sense and finite as a module over itself, as a regular module. And this theorem says let F be a simple fusion category. Then the following are equivalent. So one is what's called a spherical structure on F. And in fact, it's conjectured that spherical structures always exist on any fusion category. And the second is SO3 invariance structure on F plus a compatible SO3 invariance structure on F as the regular module. So that puts spherical in these terms and tells us in the corresponding field theory, in this case the Toraja-Viro theory, that if we have a spherical structure, we get, in fact, a theory of oriented manifolds. Okay, so again, lots more details in the paper. I think I'll stop there. Thank you all for your attention.